Okay, here's a recap of today's notes. So today's about one proportion z intervals. We've done one proportion z tests, and I'm going to tell you what the idea of the z interval is. Let's pretend I want to know something about a population. So I want to know what proportion of FHS seniors awoke before 7 a.m. today. So one way I might estimate that, I'm not going to survey all of the seniors, is I could get a random sample and ask the sample, what proportion of you guys awoke before 7 a.m.? And that is indeed what we did during second block. So in second block, 11 people said they awoke before 7 a.m., and there were 33 people in the class. So that lets us find a p-hat, which is 11 over 33, which is 33%. Okay, so this is called a point estimate because it's an estimate of the thing about the population we care about, but it's just a single number, and that's what makes it a point estimate. Just to practice a little bit of vocab here, what we've done is we have used a sample statistic, that's the p-hat, to estimate a population something parameter. So we've used a sample statistic to estimate a population parameter. Okay, so a point estimate is all well and good, but you would expect that this would come out differently for every single sample that we take. You know, in fourth block, if I ask the same question, p-hat is probably going to come out differently because of sampling variability. So instead of a point estimate, let's give an interval estimate. An interval estimate is also just what it sounds like. It's an estimate of the population parameter, but it's going to be an interval. I'm going to say we estimate that the true proportion of seniors who woke before 7 is between 31% and 35%, something like that. It'll be an interval. So let me show you two ways that you can report the interval, and then we're going to focus in on a specific calculation. So interval estimate might look like this. There's two different versions. You could say our estimate is 33% plus or minus something. So like plus or minus 10%. So we would say 33% plus or minus 10%. And that's a way of reporting the interval. And you could think about that as giving like the center of our interval. So we guess 33%. And then this is what's called a margin of error. And our margin of error is 10%. And we might be 10% lower or 10% higher. The other way of reporting an interval is giving the kind of lowest value and the highest value of the interval. So we would say between, here 33 minus 10% is 22%, and 33 plus 10% would be 43%. Oh, sorry. 23% and 43%. So this represents the same interval. It's just two different ways of describing it. One is the center, plus or minus a margin of error. The other is from a low value up to a high value. Okay, so that's an interval estimate. So the question, though, is if you're going to go from your point estimate in the middle to an interval, how do you know what the margin of error was? You know, I sampled 33 people, 11 of them. Does that mean I have a big margin of error or a small? I don't know. So that's what we're going to talk about right now. So I'll write the equation first, and then we'll talk about what it means. So p-hat is our point estimate, plus or minus z star is a symbol, and then I'm going to write SE here, although we're going to see other symbols for this later, because SE is the symbol I've been using. So this is how you calculate the margin of error. It's two numbers multiplied together. Z star is going to be a number, standard error is going to be a number. Okay, let's look and see what each of these mean. So the Z star number is related to how confident we want to be. So let's have kind of a little sidebar here. There is a relationship between how confident we want to be and how big our margin of error is. So let's say I want to be very confident that the true population proportion is inside my interval. Here's an easy way for me to do that. If I make my interval extremely large, so I'm like 98% sure that the true proportion is between 3% and 97%. Okay, wow, 98%. That sounds very certain. How can I possibly be so certain? Well, it's because my estimate is not very precise. My estimate is between 3% and 97%. So yes, I am relatively sure that the true proportion is, not 1% and it's not 98%. But this isn't really saying very much. This isn't very helpful. Let's think about the flip side. I think the true proportion is between, let's see, 32.5% and 33.5%. So that's like very specific. That's a very narrow range of possibilities. So if I'm making a prediction in such a narrow range of possibilities, maybe I'm not that confident that that actually contains the true value, but I'm only 1% sure. So that's also not very helpful. So the intuition I'm trying to develop here is that there's a trade-off. If you want to be really, really sure, you could make yourself more sure by making a wider margin of error, because that contains more possible values. So it's more likely it's going to contain the real value. But I don't want to make it too big, because that means that my estimate is not going to be helpful. On the flip side, I could try and make a very, very, very precise estimate, but I may not be that confident it's right, and that's not very helpful either. So you want to try and strike a balance. Okay, so let's connect this kind of conceptual idea with how you actually do some calculations. So this z-star number is a number that's related to the level of confidence we want to have that our interval contains the true population proportion. So let's pick a confidence number. It could be, I want to be 68% confident, or 95% confident, or 99% confident. So like, pick a confidence level. And it could be whatever you want, but these are some conventional values. So let's pretend I want to be 95% confident. What you're going to do is you're going to look at the standard normal distribution. And we want to find a z-score where 95% of the possible results are between those two z-scores. And this is supposed to be symmetric around 0. So this is going to be like whatever number z-star is, this is negative z-star, this is positive z-star. So for example, if z-star was 1, this is between -1 and +1. Okay, so if 95% of my possible outcomes are inside here, the question is, how do I know what this number is? And that's what invnorm lets you figure out. So the inverse normal function, we're using the standard normal distribution. So we've got a mean of 0 and a standard deviation of 1. This number is what area is supposed to be to the left of the value we're looking for. So if I'm looking for this z-star value, I want to know what's this area to the left. Well, I have to do a very small amount of thinking here. 95% of the area under the curve is in the middle, so that must mean there's 5% left over. Because it's symmetric, that 5% has to get evenly divided between these two sides. So that must mean there's only 2.5% to the left of this z-score. So 0.025. So we calculate it using invnorm. I guess I'll just demonstrate doing that here with my calculator. Oops. So here we go. second distribution, inv norm, 0.025, and then a comma, and then a 0, and then a 1. And so I'm getting 1.96. So this is 1.96. You might think, wait a minute, it said negative 1.96. 1.96 describes this number. This would be negative 1.96 on this side. And you can use either one, because where we're plugging it in up here, we have plus or minus anyway. So if I use the positive z, I'll end up with a plus the positive z and also a minus the positive z. If I plug in the negative version, I'll have like negative 1.96, and I'll have plus negative 1.96 and minus negative 1.96, which will turn it positive. So what I'm getting at is either number you plug in, because of the plus minus here, you're going to get both versions. Okay, so we've got our number. Now let's find standard error. So before, if we were doing a hypothesis test, the standard error was p times, p times 1 minus p over n. Let's think about why we can't use that here. Think about, what does p mean? What does n mean? N is no problem, because that's just the sample size. We have that. But p is supposed to be our null hypothesis population proportion. But here we haven't really formed hypotheses, because we're not trying to say, let's assume the true answer is something and see if we can reject that assumption. Here we're just trying to come up with an estimate. And we don't know what the true population proportion is. If we did know what it was, we wouldn't be doing the estimate. So we're going to estimate what the true proportion is using the best estimate we have, which is p hat. That was the point estimate. So even though we don't know the true proportion, our sample said 33%. And so we'll say, let's pretend that is an accurate estimate of the true population proportion. And so now we're going to calculate the standard error. And when I calculate it, let's see, it'll be 0.33 times 0.67, and then divided by my sample size of 33, and then I'll take the square root. So 0.082. 0.082. All right, so at long last, I have found these two numbers, which I'm going to multiply together, and that's going to give me the size of this margin of error. So I'm going to rewrite my estimate down here. My estimate was, my p hat was 33%. My margin of error is 1.96 times 0.082, which equals 0.16, so 16%. So my margin of error equals 0.16. So now if I was going to report my interval using a low bound and a high bound, I might say something like this. I'm 95% confident the true proportion of seniors who awoke before 7 is between, let's see, 33% minus 16% is, you could probably do that in your own minds, 17%, and 33% plus 16% gives us 49%. Or you could notate it this way, 0.17 and 0.49. So this is our kind of final conclusion. Okay, let's think about this in context. 17% to almost 50%, that's a fairly large range. So, you know, we might not feel like we've learned very much based on our sample. That feels real hand-wavy. Like 33% of our class woke up early. And so now we're like, oh, you know, probably, you know, between 20% and 50% woke up early. You know, not groundbreaking. But that's because we wanted to be so confident. If we were willing to be a little less confident, this interval should get a little bit narrower. What you would really hope is, wow, could we be more confident and also have a smaller guess interval, a smaller estimate interval? And the answer is, yes, you can. Let's think about numbers. Let's think about if we want to make, this margin of error is just two numbers multiplied together. So if we want to make this whole thing smaller, how could we do it? Well, we could do it if we made z star smaller, or we could do it if we made the standard error smaller. Okay, how could we make z star smaller? Z star is only going to get smaller if we have this. So z star describes this number. If this number is closer to 0, that means z star is getting smaller. But that's only happening if less of the area is between the z-scores. And remember, that area was our confidence level. So if we make our confidence level 68%, if only 68% needs to be here, we've got smaller z-scores, which means a smaller margin of error. But we've already said that. We've already said that you can make a smaller margin of error by becoming less confident that you're correct. So let's not think about that side. Let's think about the standard error side. If you look at how it's calculated, what's the thing that we have control over here? P hat or n? We don't really have control over p hat because that's our sample statistic. That's going to be whatever it's going to be. How many people we ask, that we do have control over. So if I asked 1,000 people, whatever this number in the numerator is, now I'm going to divide it by 1,000. That's pretty big. And so if I divide by a really big number, this is going to become a very small number. And if the standard error is a very small number times z star is still going to be very small. So I'm going to get a much smaller margin of error. And I think you have an intuition about that also. If I asked 10 people, what time did you wake up? You wouldn't be really confident in my estimate. If I asked 1,000 people, what time did you wake up? Now you can be very confident. But this equation justifies that intuition that asking more people is better. Asking more people results in a smaller margin of error, which means a smaller overall range in which the true answer might fall, even for a fixed level of confidence. So that's some calculations. That's a lot of the intuition behind them. And that was the notes for today.